Good morning, everyone. Today, we actually will continue our discussion for separation of variables. After today, we will have perhaps 1 or 2 lectures, depending on how fast we go, on the spherical coordinates when you are working on the Laplace equation. So what we have discussed previously in our previous class is giving a boundary conditions, and we're trying to calculate the potential inside the metallic gutter. So let me share my screen with you. Just 1 second. So we worked on the first half of this problem, right? We tried to get as far as we could. Given this distribution, we said the potential is a function of x and y only, because your conductors are extending infinity in z direction, so the potential has no z dependence. And the Laplace equation becomes the second derivative of the function x plus the second derivative of function y equal to 0. And these two has to be both a constant, right? And discuss that. And in this particular boundary conditions, we need C1 to be negative. So C2 has to be positive. A negative second order differential equation give us a sine and cosine combination for the solution, and a positive constant for that particular second order differential equation give us e to the ky plus e to the negative ky combination. So you can see that this is what we got from our previous class. But we're not done, right? We still need to continue solving for the final solution and figure out all these constants. So what we need to do is apply the boundary conditions. You realize that applying the boundary conditions here is very similar to what we do apply initial conditions, right? With, for example, back in 1510, if we solved for x is equal to x naught plus v naught t, right? If you know x at t equals 0 is x naught is some constant, then you can plug it in and figure out what that constant is. And the same as if you know what v at t equals 0 is some other constant, you can plug it in and you get your equation for your position, right? So this is very similar to that. You have found a solution, but you have these constants that need to be determined. So you're going to use your boundary conditions to find and determine these constants. So we have A, B, and C, D, all these 4 constants. So let's apply the boundary conditions now. So let's use all our boundary conditions, and we said we have 4 of them, right? So let's see the first one. First one is the left wall at x equals 0, v is 0. So at v, x equals 0 is 0. Let's plug that in. So this is for x, so you have to plug in for the x function. So a times sine of 0 is 0, but b times cosine of 0 is 1, right? So this must be 0 on the right hand side. So cosine 0 is 1, so my b is 0. Okay, all right, which means the x function is now simplified to be a sine kx. So it's a sine function only. So I applied the first boundary condition. I found one constant, right? B, that is 0. Now let's find the other one. The other one, I'm going to apply the one that is physical. As y go to infinity, your v has to be 0. So v, y go to infinity is 0. And you can see you need to apply to the y. So y go to infinity, d to the negative ky is 0, right? But the first term is not. So in order for that to be 0, you need c e ky at y is equals infinity is 0. E to the ky is not 0. So the only way for that to work is c is 0. You don't even have that term, right? For large y. So that the y function is now simplified into d e to the negative ky only. Okay, so I found another constant. So, okay, before we do any further, let's look what the potential looks like. The potential is the x times y, right? The function of x multiplied by a function of y. So it's a times sine k of x multiplied by d e to the negative ky. So a and d are both constants. I'm going to put a and d together and call it one constant, c prime. Okay, all right. So I've reduced the number of constants I need to solve. Right now I have only one constant I need to solve. We still have boundary conditions we haven't applied yet. So let's continue. We have the right-hand side, x equals a, v is 0, right? So if we plug in vx equals a, now you can just plug in here. Okay, so what does that look like? It looks like c prime sine k, ka e to the negative ky is 0 for any y, right? For any y. So now at this point, this can be 0. You need these to be 0. So what can we do? Can we set c prime equal to 0? Can we do that? If we set c prime to equal to 0, you realize this whole potential function is 0. That's not okay. That is a trivial case. Well, it might have satisfied if everything is 0 inside. If you set c prime equals 0, you're saying everywhere is 0, right? Because that constant c prime is 0. And that is a problem because, okay, even if it satisfies boundary condition on the left and right-hand side of the wall, it doesn't satisfy what's on the bottom. The bottom is not 0. So that is not okay. We can't do that. So we need the sign of Ka to be 0. That we can do. So we need to set sign of Ka to be 0. So that means K and Ka has to be what value? Sign of something is 0, and that argument Ka needs to be
n pi.
Yeah, n pi. Yes, n could be 1, 2, and 3, and so on and so on. So that our K is now n pi over a. Okay, so okay, another K is another variable that we haven't figured out before, but now we did. So this is our separation constant, K. Okay, so the last boundary condition, we have used 3 already. The last one, well, before that, let's sort of regroup our solution one more time just to see what it looks like. So far we got vxy is c prime e to the negative ky sine of kx. But k is, we already know, with k equals n pi over a. And n is 1, 2, 3, and so on and so on. Now, k could be negative, right? N could be negative. N could be negative 1, negative 2, negative 3. If n is negative, it's really just changing because sine of negative x is negative sine of x. So you just have a negative sign in front of everything. So c prime becomes negative c prime. So it is still just a constant, right? We're not going to consider as a new solution. So we're just going to write 1, 2, 3, and so on and so on. All right. And could n be 0? So if k is n is 0, sine of 0 obviously is 0, but e of negative ky now becomes, k becomes 0, right? So this becomes 1. So your v become a constant. And that's not okay because you need v to be left and right hand side of the wall is 0 and on the bottom is some other value. So if v is everywhere is the same constant, that's not going to satisfy those boundary conditions. So n is 0 is not okay, right? So you eliminated that during the process and figure out Right, that's why we only write 1, 2, 3, and so on. So this is our solution we got so far. So we are just one step away from getting our final answer. We realize that's the fourth boundary condition. That's the bottom one. So the bottom one is y equals 0, v is some given function of x. Now this could be a constant or could it be some function like ax plus b or blah, blah, blah. So a y equals 0, what would this become? You realize, let's apply this last boundary conditions to the newest solution that we've got. I got a question, why would v be constant and not 0 if sign is 0? V cannot be, I'm saying v cannot be 0 everywhere, either can v be constant everywhere. Because you need v to be 0 on the two walls, right? And some other value on the bottom. So if you say v everywhere is 0, doesn't satisfy v is some other value on the bottom. If you say v is a constant everywhere, well, obviously left and the bottom, the left and right and the bottom are different values. So you can't set v to be constant everywhere. Did that answer your question? Okay. All right, so our last boundary conditions, let's plug it in, y equals 0. So y equals 0, this term is 1, right? This becomes c prime sine of kx, gotta be some kind of a given boundary condition. We don't know what it is. And the problem may choose to give you whatever function they like for v of naught, v naught of x. Okay, look at this and see what are we going to do here. You might wonder, well, to make them match, does that mean I have to set my bottom wall to be a sine function? It doesn't seem to be the case because I can build this setup the way I want, however I want, because I can always ground the left wall and the right wall. I can always put in, okay, insulated from the bottom wall, and I always can make sure whatever V I want the bottom wall to be, I can always force it to happen. Then that will change my potential in the middle. So I can set this V, you can set this V, whatever you want. So it doesn't have to have a sine format, right? At this point, are we stuck? Obviously, there we are not, right? There is a solution here. The idea is that even though for one c's of prime, you cannot make this to be exactly, let's say v is just simply a constant, right? Or this is 2x plus 3. Let's say you can set it however you want, right? For one of the c prime, even though you can't make this work, but for a combination of them, you can always superpose them together and make it work. So let's, before we go any further, I want to further illustrate my point, but let's look at this particular multiple choice question, okay? All right, so let's say we have V1 and V2. They both satisfy the Laplace equation. And does A times V1 plus B times V2 also satisfy the Laplace equation? And I will let you guys vote here. Okay, seems like I have gathered the majority of the vote. So any last minute vote before I close it? Okay, if not, I'm gonna go ahead and end this. All right, so this is your result. We have a majority voted for A and there are quite a few voted for B as well. So let's think about B. What about B? The uniqueness theorem, right? That is something we did emphasize quite a lot in the previous class. It says if you cannot have two independent solutions, didn't you tell us that we have to guess what the solution is? And if it satisfies boundary conditions, then must be the only solution. But now you're telling me you have one solution, two solutions, and three solutions. So what about B? What do you think about B? What does the uniqueness theorem says? Can anybody state the first uniqueness theorem?
If I recall correctly, it says that given some conductors within a region, if you have a potential or a boundary condition, then there must be only one unique solution to either Poisson's equation or Laplace's equation.
Yes, very good. Uniqueness theorem says not only this solution satisfy here your Laplace equation, it also has to satisfy all the boundary conditions. If all of those are satisfied, then that must be the one unique physical solution possible. Here, all it's telling us is these two functions are the equation to the Laplace equation. We don't know if they all satisfy the boundary conditions, right? So that doesn't really limit us. If it's not satisfying the boundary conditions, it doesn't limit us to the one unique solution. All right, someone asked for the exam. It opened before I forget to tell you at the end of the class. Let me just answer it here. It will open on midnight on Wednesday, and it's available the whole day of Wednesday. It covers material only chapter 1 and 2, not the chapter 3 that we're talking now. We will not have class Wednesday, but I will open my lecture window just in case if people want to jump in and ask questions. Okay. All right. So that's back to the question. All right, so in this case, no, we are not limiting us to one solution because there are not boundary conditions not satisfied yet. And A is correct because Laplacian is a linear operator. So if you have the new solution, plug it in, simply see if it still applies, right? This one is become A1, Laplacian of V1 plus B2, Laplacian of V2, right? Each of them set is zeros. This is 0, so it's become 0 plus 0 is 0. So this is also a solution to your Laplace equation. So a linear combination of these solutions is still a solution. So what I'm trying to say is our final solution, I'm gonna start new page. We want to have a combination of C's, okay, C's of n's, and it's the next is a sign of kx, right? K is n pi over a, right? So n pi over ax, and have your e to the negative ky. Again, k is n pi over a y. So it's a linear combination of all of these combined. Whoops, my screen is not updated. Let me share it one more time. Your exam is you need to write it on a piece of paper and then once you're done, you just upload it. Open response. Yeah, so there are 3 short problems and 3 longer problems. So you just write on a piece of paper and then upload it after you're done. Okay. It's similar to the practice exam that I have already posted. So what you want is many of these combined V. 1, 2, 3, blah, da, 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 from this to infinity. Because if it's a combination of these, then the last boundary conditions can be satisfied. Because once you want y equals 0, this is the bottom law, is have some kind of particular function. You can always set this y equals 0 equals v naught of x. You can always pick your combination of a series of C of n, the constant, so that this boundary conditions is satisfied. So it is always possible. And you can set your boundary to be however you want, right? And your solution has just to change to match that. So, and then at this point, we do need to put a little pause again, even though it's last step, it's still not quick enough. We have to do something called Fourier's trick to be able to fully solve what C's of n is, okay? You probably have already heard of this, that for any given solution, you can always expand it as a superposition of sines or cosine functions. And this is the Fourier's trick that we are going to use to solve for the constant C's of n. All right, so let's do it. Before we do that, there's a little bit math that I want to briefly mention. So the functions of sine functions, they are a complete, and they are also orthonormal sets of functions. So when they are orthonormal, meaning that the integral of fx gx dx is 0. Right, so sine of functions are such a function that they are orthogonal to each other. So when you do an integration for this particular sine function, then prime integrate from 0 to a is going to be 0 if n is not equal to n prime. But if n is equal to n prime, you get a value that's a over 2. You could verify this yourself after class. Just set them to be equal, so this becomes sine of n pi x over a squared. Right? You can change that into 1 over 1 minus cosine of something, and this can be related to cosine 2 of x. You can just go ahead and verify that later after class. So unless that they are equal, this integration becomes 0. Okay, all right. So let me, let's do a quicker question about sine function. What is the value of this particular integration? I'm gonna give you a relationship that might be relevant. You may want to use it, or maybe you decide not to use it. Sine of nx, sine of mx is equal to cosine n minus m x minus cosine n plus m x. Okay, so that is a relationship you may want to refer to. So go ahead. If you want to calculate it here, you can, I don't think it needs to be discussed in the group. So I'm gonna open up my polling, let you poll, but you can take a little bit, you can take a minute to compute the answer, feel free to do so, okay? I got a question asking whether you could check it on Mathematica or calculating it. It's okay if you use Mathematica here. It's really, I know you, I already know that you know the answer, so it's okay. All right, another 15 seconds. So if you haven't voted already, please consider putting your answer in there. Okay, all right, I'm going to close this. All right, so we've been talking about the sine functions being orthonormal, so that unless your n is equal to n prime, in this case are two m's, right, n and m, then they're going to be zero. This is, you can use this identity to help you verify this, that these two functions, the integration becomes cosine of negative x dx, and you have or minus, sorry, cosine of 5x. But no matter what, each of them becomes 0 when you do the integral. So it's going to be 0. Okay, so A is the correct answer. All right, so unless n is equal to n prime, you will get 0. And that trick is going to help us when we find our last constants for C. And actually, it's not one constant, it's a series of combination of C's of n's that we will find by using this trick. So exactly how are we going to do this? Well, going back to this problem, recall, this is the problem, right? And what we got previously is V naught X. So we will solve a particular case when the last boundary conditions on the bottom wall is a constant. It doesn't have to be, but what happens if it is a constant? So how are we going to solve this? Okay, so previously, recall what we got is that, let's go back, scroll back to see what we have there. Is this, right? So we know that what we want to pick for C's of n's, now y equals 0, this become 1, is equal to this particular case. Okay, and now we said this V naught is V naught X is V naught. Let's go back here. So the fullest trick, and we're going to do this. We're going to multiply both sides by sine of n prime pi x over a. Okay. And we're going to, next step, integrate it from 0 to a. Okay. All right. So all we are trying to do is we wanted to be able to like peel the Cn out of this big mess. Okay. And by multiplying both sides by sine and do the integration, we're able to pick Cn out of it. So the right-hand side becomes, let's see, C's of n, 0 to a, sine of n pi x, sine of n prime pi x over a. And this we know, right? We know that for n equals n prime, it has a value of a over 2. And n, for all the other n primes, it is 0. So you can see that you're able to separate and peel the C's of n outside of that really complicated linear combination with sine. Okay, so C's of n is going to be calculated, divide the a a over 2 to the other side, you get 2 over a. Now the other side is 0 to a sine of n pi x over a. Now you only want the n prime to be the same as n, so this n prime becomes n, right? So n pi x any kind of function you want, dx. So any given v, you can pick out the Cn that you need. This is the Fourier's trick. But I said I want to set this v to be v naught, right? All right, so now you set it to v naught. You can really finally be able to solve this. So, okay, so now you have set v, just a constant on the bottom wall. What does this look like? Okay, C of n is 2 over a sine of n pi x over a constant, so v naught dx. Well, it's a constant. I'm really just integrating the sine of n pi x. Really just doing this integral, right? And I know how to do this. I know that for this last bit, it's going to give me cosine of n pi minus 1. And there is a negative sign come from the integration. So I get this. And you can see that for different n's, now things become a little bit more interesting because for n is equal to 1, okay, cosine of pi minus 1 okay, n equals 1, 2, 3, and so on and so on. Now you can see if I pick all the odd numbers versus I pick the even numbers, if I pick the even numbers, this will go away. If I pick the odd numbers, it will double my result. So if I pick the even numbers, cosine 2 pi minus 1, I get 0. If I get 3, cosine 3 pi minus 1, I get negative 2. Right, so I have this pattern so that you may be able to simplify your solution just one step further to be a little more organized. So earlier we had a combination of n from 1, 2, 3, and so on and so on. But now you realize that all the odd part survives, all the even part goes away. So your final solution will become something like this, where you pick only the odd ends. So n is 1, 3, 5, 7, and so on and so on. Again, and let's see. So all the 4, okay, I haven't finished this. 4, n equals 1, 3, and 5, and blah, blah, blah. This becomes a 4 v naught over 8, right? Because this is 2 v naught over 8, and this is negative 2, right? So it becomes 4 v naught over 8. So I have 4 v naught. Okay, let's plug it in. I don't want to jump steps. So this, because this is a complicated calculation. All right, so C's of n's is 2 over a times this result, 4 v naught over a for n is only odd, okay? All right, so your v is going to be all of the odd. I should cancel my a. Sorry, I may have messed up a over 2 versus a 2 over a somewhere. Well, let me see. Oh, I'm sorry. Okay, so I messed up here. Okay. All right, corrected. Going back to the step. Going to be negative 2v naught. It turned out when I do the integration, I get an a out of it. The a should already be canceled. I get an n pi here, cosine n pi minus 1. Okay, so I messed up earlier, sorry. All right, finally, pick out all the odd numbers from here, and I get 4v naught over n pi. And again, you have your sine function, you have your exponential for the y component. So it's going to be n pi over a y. Okay, so this is our solution. We have picked out the n we need, and we have a sine function for the x. We have the e function for the y. And this is my final solution. Okay, a little bit more clear. All right, which is also written here. So we finally solved it. 4v at the bottom wall is a constant. So we got this solution. Now, if your bottom wall is something else, what do? You will go back to this particular situation right here. Instead of plugging v naught, you plug in whatever function that is given to you. And you may need to rely on Mathematica, or maybe you have to, sometimes you have to keep C's of n just in the integral format, but that's okay. Technically, you have already solved it. You know how to pick out the CNs that you want. So, but for a constant, it can be written in this relatively simpler format. Okay, so I want to further help us understand this a little bit better by giving you a few different scenarios of different boundary conditions. And let's see, pick out whichever constants that we want. Let's stare at this function for a little bit. So this is telling me it's a sine pseudo function in the x direction. It is decaying in the y direction. So so you can see that it's a sine pseudo in the x. So in this case, this is my x direction. And this is my y direction. You can see that the value for v decrease very quickly in the y direction as y increases. But in the x direction, it's kind of having the periodical pattern as the sign suggests, right? You can plot for more n's to see what this looks like. So this is for different values of n, what this v gives. So apparently the separation, the distance between left-hand side of the wall and right side of the wall comes in play when you're putting the little constant here, right? So if we were to compare two different gutters, and one is much narrower than the other, and everything else is the same, what can you conclude about the value for V in these two different scenarios? Given, obviously, given the same value for Y, if you're looking at the middle of the base in the two gutters, how do these values compare? Do these values the same in both of the gutters, or maybe one has bigger value than the other, or maybe two has bigger value than the other? So I want you to go ahead and discuss this question in your group. This is really just helping us understand this expression just a little bit better. Okay, now before we go off and send you off to your breakout rooms, I want to ask, are there any questions on how we find our constant C's of n and find the solution for the final solution? Because I know this is a long process, right? And you can see that I made mistakes myself in the middle for solving. So if you have any questions, please ask at this point. Any questions?
Just a quick question about when you multiplied both sides of when you were solving for C sub n, you multiplied both sides of your equation by sine of n prime pi kx over a.
Yeah.
Why did you take that approach? I'm just curious.
Why do I multiply? Because somewhere someone invented this because they know about the Fourier trick. They know that if you multiply a sine function by another sine function, the result.
Oh, okay. So they're leveraging orthogonality.
Yes.
Okay.
It's just a trick that you can imagine. C is now bundled with sine. You cannot separate it. By doing so, you're able to pick the C out of it and say, oh, I can solve for Cn and it's equal to this. Thank you for asking that question. Any other questions? Before we go to do our question, clicker question. So here's the deal. The thing is, before we apply the final boundary conditions, our solution is not unique yet. Before you apply the final boundary conditions, you may be able to find multiple solutions that all satisfy the Laplace equation, even satisfy the 3 other boundary conditions that we did. But in order for it to satisfy the last boundary conditions that the bottom one matches, you only have one unique solution, which is shown here. So this is not saying, I want to emphasize, this is not saying that you have infinity amount solutions. This is not saying that for n equals 1, you have a solution. For n equals 3, you have a solution. For n equals 5, you have a solution, and you have infinity amount of that solution. It's not saying that. It's saying you need all of them combined to be the unique solution that satisfies all 4 boundary conditions and the Laplace equation. If you pick only one of them, you satisfying the 3 boundary conditions and the Laplace. But if you want to satisfy all 4, the last boundary conditions you also want to satisfy, you need all of them combined together. So this is one solution. This is not n solutions. This is one unique final solution. So I want to emphasize that because that may be confusing if you're writing in terms of the linear combination of n's, right? All right, so if you think of any more questions, feel free to ask, but otherwise let's go back to this particular problem. Feel free to take a screenshot before you go into your breakout. Okay, so another 15 seconds. So if you haven't put in your vote, please do so. Okay, I'm gonna go ahead and close this. All right, so this is the result. So can anybody tell us how do we compare these two? Seems to be quite complicated, right?
You would pay attention to what has the most influence in your function of v, so your sine function.
You said, say it again. You said we will pay attention to what?
The, I guess, factor that has the most influence on your potential, which in this case would be sine.
That's a really good point. We wanted to pay attention to a function that has the most influence. So sine, one is the sine function, one is the exponential function. So which one will have more influence?
The sine, I would argue,
And why is that?
because your exponential would just be a constant.
And why is that?
If we had, I mean, I may be wrong, if I may be forgetting my math methods, but for what I recall, an exponential can only be broken down into cosines and fines if it's complex, and it's not. So it's only, I mean, it's only a number.
It is a number, but it's a very, could be a very different number. For example, e to the n is of 0 is 1. Y equals 0, for example. Okay,
Mhm.
e to the negative 10 will be something else. E to the negative 100 will be something else. So here you can see y equals something. Let's just say y equals 10, y equals 100. This is negative e to the negative 1. So it's a function. As y pick on different values, e to that power give you different values.
But I beg to argue, if we were to look at the argument of sine, and I don't know, just plugging in some numbers, right? Let's say if x is equal to 4 and n is equal to 1, we would have some even multiple of pi, which would make sine 0.
Yes. And
Well, because if we have, I mean, no matter what multiple of n we have, whenever it's multiplied against 4, we get some even multiple of pi, so sine will always be 0. Or is that just flat out wrong?
no, it has to be, it has to x has to be exactly make n, you have to make n pi x over a to be the n pi's in order for the sign to be 0, right?
Yeah. Yep. Yeah.
Other x, you will not have a 0 sign. Yeah. So it's a very good point. We have to see which one it dominates. And I would argue that the sign is periodically oscillating. So yes, you can have x be varied a lot, but you may end up with the same value because it's oscillating, right? Because of a sine of pi n pi x versus sine of 100 n pi x, when x equals some value, x equals a, give you actually the same result. So in the sense that it doesn't really oscillate all that much or change your value all that much in the x direction. So let's go back to the graph as I was trying to show that this is your x direction. So you can see it doesn't really change all that much, but in your y direction, exponentially decay happens very fast.
Right.
You
Got
shift
it.
the y a little bit and you have changed your value a lot. So because of that, I would argue the one that is dominating is the exponential term, but not the sine. So now you can see if that is dominating and what we're changing is the a value, right? One has something that e to the negative n pi y over a is 1, and 2 is e to the negative n pi y over 4, right? So which one give you a bigger value? without the minus sign, 1 give you the bigger value, right? With the minus sign, then 1 is 1 over that, so 1 give you a much smaller value, right? Yeah, so in this case, it's divided by a bigger denominator with a minus sign. 2 is much bigger. Okay. So in this case, we will choose item E is the correct answer. Okay. Any questions?
When we're doing homework problems like this, I mean, would there be any way to have some level of intuition into the problem without using Mathematica to graph the function?
Well, for this, you don't need to know, as long as you know in the x direction is a superposition of a bunch of signs, and signs is like oscillating. So in the y direction, you imagine it.
Got it. Okay. Got it. All right. Thank you, Dr. Ryan.
Yes, thank you for asking that. All right, so okay, finally, here comes, I would think the next few questions more fun, because that is actually using the boundary conditions and picking out what the constants that we need. Before we do that, just one little bit math is something regarding this sinh and cosh. Okay, so one of them is a sinh function, one of them is a cosh function. And if we don't remember what these functions are, I'm gonna write it out for you. This is sinh, and this is cosh of x is e of x plus e to the negative x divided by 2. So these are the two functions, okay? All right, so given that, which one is which? Can you pick out, separate one from another? Okay, and if you wish to discuss, maybe a minute or two, less than 2 minutes in your breakout rooms, okay? All right, I've gathered majority of the vote. Just more 5 more seconds if you haven't voted already. Okay, all right, I'm going to go ahead and close this. All right, so seems to be an agreement. A majority of you agreed on curve 1 is the cosh function, and curve 2 is the sinh. There are more than one ways to figure this out. Anybody would like to share what they thought?
You can just looking or just visualizing or graphing each of the x, you've got some I don't want to say exponential growth, but let's just say it anyway, exponential growth, and then e to the minus x is exponential decay.
Okay.
So if you kind of add them together, you get some sort of parabolic curve. So the only thing that would be added together would be cosh. 1/2 is just a factor, and just by deducing, if you think cosh is this parabolic curve, then the other one must be sinh.
Okay, so looking at each of the graphs separately and see how they would add up to be whatever that you end up with. I would say if you can do that in your head, that's wonderful. I
cannot. I use Desmos.
I find that maybe not as obvious as we would like it to be. Is there another way that maybe a little bit easier to figure out?
I thought
Go ahead. Sorry.
my bad. But I thought cosine is just a positive function all around, like it can't be negative, so it has to be above the x-axis.
Okay, so this can never be negative by observing the behavior. E sub x positive, no matter what value you give, is negative x positive. Yeah, so it always has to be a positive function. We actually have, you guys have come up 2 ways. I originally thought of 2 ways, actually 4 ways. Very good, Charles, thank you. Kenneth, were you gonna say another method?
I was gonna say the same thing.
Okay, cosh is going to be a larger than 0. All right, so you guys have 2 ways. One is to look at ex, e negative x, the graph, and combine them. The other way is no cosh that is positive value only. I'm going to present 2 other ways. Is that I claim that cosh is a even function and sinh is a odd function, right? Because cosh of negative x is e to the switch the x to negative x, switch negative x to x is itself, right? But the sign, the sinh, the negative x becomes e to the negative x minus e to the x, which is negative of the sinh. So which one is, well, this obviously is a even function, and this is an odd function, and I know how to separate them. The 4th method is to look at particular points, right? At x equals 0, simply plug in 0. This is going to be 0, and this is going to be not 0, which is 1. Okay, so x equals 0, the function has to pass through y equals 0, and that is going to be your sinh. Okay, so B is correct. Very good. All right, so we know how to pick these functions. Now, finally, let's use them to solve more boundary condition problems. So here, this is your boundary conditions. Imagine you have 4 walls. The top and the bottom are grounded, kept at 0. The left and right hand side kept at the constant, which is V naught, a constant voltage. So we want to find the potential inside. Okay, so you have 2 directions, x and y. Which one of the coefficients has to be? So for the x, what do you think it will look like? Would it be a cosh function or a sinh function or combination of them? So I'll let you again discuss this for a couple minutes. Okay, 10 more seconds. All right, so I'm gonna go ahead and close this and we can take a look. All right, so it already picked out the positive constant for us that has to be the x direction. Now recall we said if you have this 0, 0 behavior, right? That is telling us these constants in that direction has to be negative. So you have a sine or cosine combination for the y direction. But for the x direction, it tells us it's this particular format. So a lot of you picked out a pure Cauchy function, right? Some of you picked, well, maybe you should write it in terms of the e's of kx and the e's of e to negative kx, because that was the original expression that was given, right? Okay. So for those of you pick Cauchy, how do we know that a has to be 0? The sinh has to go away. What kind of behavior in this boundary condition tells you that?
Well, I saw that at negative a over 2, it's v naught, and at positive a over 2, it's v naught, and that's sort of the behavior of the Cauchy function.
Yes, yes, exactly. So as x pick out a negative value, your does not change your potential. So the potential has to be for the x direction has to be a even function, and it has to be pure Cauchy for that even function to work. So yes, A is correct. Now, if you're curious, why don't we write it in this format? In fact, when you're solving this problem, you can start out writing this format or this format. They're equivalent. Okay. And if you start out with this format and you plug in the boundary conditions, k a over 2 plus b minus e negative k over 2 is v naught, and you plug in the negative k over 2 and negative k over 2, you realize a has to equal to b, so that if you can write this in front of everything, sorry, k plus, and this can be written in terms of Cauchy. So you will end up with a Cauchy function eventually, but you can simply start out with your solution like that, but you don't have to. It's not like you must write it in this way. If you're familiar enough, you will start out with a Cauchy function right away, or you may start out with this combination and then decide a is 0. Okay, so these two are equivalent. Okay, these two. One last question. This will be real quick. Okay, so here I have v naught on 4 of the walls. What does it mean for C1 and C2? Which one has to be positive? Which one has to be negative? Because now they're the same. Now you might wonder, okay, they're all, if they're different behaviors, it makes sense to assign one of them to be negative and the other one to be positive, right? But now they are exactly the same behavior. V naught here, V naught there. So what would you predict? Take a wild guess. The only way for that to happen is the C1 and C2 must be the same, right? Because the same behavior in both directions. So if they're the same and they add up to be 0, each of them has to equal to what? What value?
Would it be 0?
Yeah, they would just have to be 0. That's the only way for this to work. Now C1 and C2 must be 0 here, because in X direction, Y direction, exact same behavior. And when you solve, anybody care to guess what is V in the middle? You can always guess. And if it satisfies the boundary conditions, it must be the unique solution. Just take a guess. Whatever V has to be, when it goes to this side, it need to become V naught. When it goes to this side, it need to become V naught. When it goes to the left-hand side, it need to become V naught. When it goes to the right-hand side, it becomes V naught. So what must be V in the middle? Yeah, it's just V naught. It turned out to be a constant everywhere. That's the only possible way for this to work. And you can see if C1 and C2 are constants, are zeros, meaning my potential is a constant, V, X and Y inside is just a constant, right? Then, you know, 0, 0. You cannot get X as a function depending on X. It's just a constant. All right. So you have a pre-flight that was due today at 12 p.m. I don't know if you have done it, kind of just cut past our class time, but I believe that after we have discussed this, you may want to revisit some of the questions. If you have difficulty, you can look at those questions again, and we will go over those pre-flights and next Monday when we meet. All right. So I'll see you guys. If you want to ask me questions, you can. I'll open up my chat. I open my class Zoom on Wednesday at the same class time, just in case anybody run into technical difficulties or anything. Okay. Otherwise, I'll see you next week. Okay. Bye.
Thank you, Dr. Ryan.
Bye, everyone. If you wish to redo your pre-flight, let me know. You email me separately. Okay.